All right, line V1, learning task 5. We are going to start by taking a look at primary impedance, or Z, types of starters. First of all, let's go and define what impedance, or Z, is. Impedance is going to go and be a combination of actual pure ohmic resistance as well as a combination of our inductive reactance, or inductive well, it could be inductive reactance or capacitive reactance that we could go and have. Ultimately, we don't use capacitive reactance. We're going to go and use inductive reactance. But when we talk about primary impedance, we're talking about one of these two that we're going to go and use to create a very large value of blocking for our current. And we're going to go and place that large blocking in line with our motor. Either it's going to be a resistor or a reactor, so this component inside of here could be changed to either one of them. We don't know which, but it doesn't make much of a difference to us. Ultimately, it's going to be placed in the same mannerism. And over here, we're going to go and see that we've got, once again, two sets of contacts. We did that timing diagram on the previous video where we took a look at the difference between open transition and closed transition that we could go and have. And where we said that we are going to go and have start and we are going to go and have running that are going to go and be energized at different times. In some cases, we are going to go and have closed or open types of transitions. What they're showing us over here is a one-line diagram showing just, it could be either line 1, line 2, line 3, but they're saying every single one of our lines is going to go and have a starting one that is going to apply power. If I were to only close that start, I would see that the only path for power to the motor would be to go through that resistance, which would mean that we would have a series type of configuration between this value of resistance and the actual motor winding that it's feeding into in that motor itself. So we would drop some of the volts over here, and the remaining volts we would go and drop across our motor, right? We know that our source voltage is going to have to be made up of these two. According to Kirchhoff's law of voltage, the sum of all voltages is equal to my source voltage. So I'm going to have the volts across my resistor and the volts across my motor. Together will equal my source voltage. This is going to mean that I'm going to have a smaller value of volts that this motor is going to be starting up underneath, which means it's going to be a reduced torque, but it's also going to go and have a reduced amount of current because my overall impedance of this circuit, my motor winding and my resistance here, is going to be much greater. Once I get the motor somewhat operational, coming up to speed, etc., then what I'll do is I will go and close this run winding, and when I do that, my current is going to go and transition from that top yellow path that we saw over there. We're now going to go and take the path of least resistance going through here, which ultimately means that we would be losing any sort of current going through that value of resistance, which would mean that my source voltage is going to get dropped all the way across only the voltage of the motor itself, or the motor is going to go and have a full value of voltage placed across it. What we'll do is we will select this value of resistance that we are going to go and have in here to go and limit my motor voltage. Now, we do want to go and limit it. We don't want to take it down to or limit my motor voltage so that it can limit my current. We don't want to take it down too low. We saw what happened when we went and squared 50% voltage in the previous one, that we were only at 25% of our startup torque. So usually we're going to want to go higher than that because it's a squared value. It actually makes a fairly large difference in increments between 65% and all the way up to somewhere around the 80%. We could take these and we can square them. We can see what that's going to give us for startup torque. Let's just quickly do that. 0.65 squared gets me a value of 42% that we would go and have. So we'll just put that there, 42% torque. All the way up to 0.8 squared, which is going to be 64%. So somewhere between 40 to 60% torque is really what we are going to go and see out of most of these. And that's going to be 40 to 60% of the startup torque. So if my startup torque was 300%, the design D, 300%, I would take that 300%, oh, that's a backwards percent sign. That 300%, I would just multiply it by whichever one of these I was using, and then that would tell me what my actual startup would be off of it. Okay, because it would go and be a phenomenally large jump in torque that we would go and see, where we're going to start, and then all of a sudden it's going to be as this motor kind of goes up like that. We don't really have a lot of times where we're only going to go and use a single step. In a lot of cases, we're going to go and have multiple steps that we're going to place in there. We're also not going to go and use, as some people incorrectly assume, a rheostat, because a rheostat would mean that I would have to go and have a wiper arm that would be moving along there. And the problem with the wiper arm is that that thing is just going to be sparking like crazy because it's not designed to carry large amounts of current through that. What we will do is we will have fixed resistors, large resistors that are going to be made out of like wire or ribbon type or graphite types, or sometimes it's just going to be compressed types that we're going to have. We're going to have large fixed resistors that are going to be bolted into the circuit, and we're just going to bypass them with contactors around them. It is also going to go and provide us with a type of startup that is going to be referred to as a closed transition, right? We take a look at what we're seeing over here in the start and run. We would see that initially I'm going to go and close my start, and then after a time, once our motor starts getting up, we're then going to go and close our run. But we see that we never have a point where this one is dropping away before the next one's going to go and apply. And what that means for us is that ultimately, both of them would drop off at the same time. I should make that one a little longer. Ultimately, what this would mean for us is that we're going to go and have a closed transition. There will always be a path for current going through here. It's also going to mean that we're going to have less controls that we are going to need to go and place into there, because if we don't have closed transitions, sometimes we can have problems from inductive kick because we got these motor windings spinning through a field and we just get boom, these kicks that are going to come back out of them. Let's go and take a look at a actual component one now instead of just looking at the one-line diagram. As a component, we should be able to recognize a number of things. First of all, we are going to go and have our power circuit, which is going to be this section over here. And then we are going to go and have our control circuit, which is going to be this section over here. Let's analyze the power section first. The power section, relatively simple. We see that we're going to go and take lines in through my overloads into the actual motors itself. Once again, the overloads themselves never are actually going to go and open, but those overloads are going to go and generate heat that is ultimately going to go and affect a set of dry contacts inside of here. 95, 96 is going to go and be our two terminals on most of our overloads that are going to be normally closed. There are other designations when we are looking at nematile, but for most of your controls, you'll probably end up IEC, so 95, 96 is the terminal designations. We recognize that one. We should also go and recognize these over here. These are going to be my main actual contacts for my motor. Main contacts for my motor are going to be fired by this coil over here. So we see we got a couple of components that are physical components in the power circuit, the overloads and the actual contacts, that are then going to be tied to control components that are going to be inside of my control circuit. Last thing that we are going to go and have is we are going to go and have a accelerating contactor. And the accelerating contactor is going to be these three over here. This one's supposed to have an A on it as well, that are going to get applied by this coil over here. Let's go through operation. Off of this one, I'm actually going to move this thing over just a little bit, and then we're going to go and put in our timing diagram right next to this thing as well. Okay, going to this one over here, let's start out. Let's start out by defining what this is going to go and be. We see that these two have got the same designation, therefore they're going to be related. They've got TR, which stands for timing relay. And when I go and examine this type, I see that this thing is going to be normally open. And I see that my arrow is operating upwards, so it is going to be timed to close. Ooh, I started to draw an arrow there. Normally open, time to close, which means that when we apply power, it's going to go and wait, tick, 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 and then boom, close my actual contact. Okay, let's go through this thing. Let's start by designating how far power can get through everything. I'm going to go and do two power lines. I'm going to go and have my main power to the motor, which I see is going to be stopped by these contacts. And I'm going to have my control power over here, which is going to go and be passed through up to here, and up to here at this point. And I'm not going to bother taking a look at the other line, okay? We're just going to go and start from the one line over here, and we're going to work our way through. There is this other component that they're showing up top over here for two-wire control. This would just be if I had something that was going to go and be low voltage release. If this whole motor was starting up off of a thermostat, or if it was starting off with something like that. I could just bypass this entire system over here and erase all of that, and I could just use a 2-wire control that I would bring up to that point, which would go and give me operation. We're not going to do that though, so we're just going to go and ignore that one for the time being. At the instant that I go and press my start push button, I'm going to go and complete my path through to the S coil and to the timing relay. So I press my start button. I'm going to go and provide power all the way through. I'm going to have a complete circuit on my controls. It is going to go and provide power to the S coil. The S coil is then going to seal itself in through here, which is also going to go and provide power to my timing relay over here. And I can take my finger off the push button at that point. So we're sealed in over here. That's going to do a couple of things. First of all, I'm going to go and examine any S contacts that I have. S contacts that I see inside of here are going to be my main motor ones. And so I'm going to be able to now complete current through to my motor over here. When I complete current through to my motor, I'm going to go and have my motor, which is running its current through those resistors. And at the same time as I apply power to the S, I apply power to the timing relay, which is then going to start timing. Tick, 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 and then after whatever the predetermined amount of time is, it is going to go and close as well, and when it closes, it is going to power up my A, and when I power up my A, it is going to go and close these contacts over here now. Those ones were already closed, and when it goes and closes those, it's going to go and divert the current around the resistance. The main motor current is going to go around the resistance to the actual motor itself in each of these. Lovely. We are now operational. We know that at the instant that we go and close power off here, as soon as we go and operate our stop button, it's going to drop out the S coil, which is going to drop out power to the motor. It's also going to go and drop out the timing relay, which is then going to drop this contact, which is then going to go and drop out my accelerating contact over there. Let's just quickly do that. Boom, we'll drop that out, which is going to go and drop out all the rest of my power inside of the circuit, and it resets my timing relay. Drawing this thing out as a timing diagram, I'm just going to go and take a look at my start button over here. And I see that at the second that I go and press my start button, and we'll just do a short little press over here, it is going to go and activate a couple of things. The first thing that we'll do is we are going to go and have our S coil over here, which is going to be my power starter coil. So we'll just call that the starter. As soon as I apply power, my starter is going to go high. And it's going to go and stay high. And I see that as soon as my starter goes high, it is going to go and start up my timing relay. And then the timing relay is going to start its timing. And after the timing relay has started its timing, it is then going to go and apply my accelerating relay. So we're just going to go and put this in over here as being T up to there. And then we see that that is going to go and be directly related to my accelerating relay, which is then going to go high at that point. Following this through, right again from the top to the bottom over here, this is now going to be my motor at operation. We've got that timing that happens inside of there. And ultimately, when I go and hit my stop, oops, sorry, this is my A coil over here. Just put in my stop. My stop would look like this, where it's going to go and start high. And as soon as we take my stop low, it is going to go and reset everything else. A is going to go off, timing relay is going to go off, the starter is going to go back off as well. We see those relationships. So anytime that you draw these, you should be able to read a diagram like this and make it correspond with what we've got over here. This is, by the way, timing diagrams are really useful when you're having to explain stuff to operators. Anybody can grasp the concept of the timing diagram. They don't grasp what you're trying to explain to them here, but if you just draw it out like this and you say, look, when I press my start button, it is going to go and start up. So I'm going to go and have my motor that's going to be operating under acceleration right now, and then it's going to go in time, and then I'm going to see that at that point it's going to go and close the accelerating relays, and my motor is going to be operating at full speed. You know, you might just go and call these things different names. If I were to go and introduce this, I would call this the startup, and I would call this the full speed. You know, and it's going to make it easier to go and explain to anybody that's not electrically savvy. Okay, this only shows a single value of resistance. We know that we can go to multiple values of resistance as well. If I go to multiple values of resistance, sorry, I got that one duplicated here for some reason. If I go to multiple values of resistance, I'm just going to need to go and have multiple accelerating relays that are going to be utilized with this, where I'm going to go and once again, at the instant of startup, we'll draw these actually out one line at a time. We'll say that this is going to be startup. And then we would have stage 1 or step 1. And step 2 will just show what's happening on each one of these. Basically, at the instant of startup, I would go and have only closure off of this one, which would mean I would be passing power through my resistors and overloads to the motor. Under step 1, we'll go through the drawing in a second. Under step 1, I would go and have this one closed and this one closed, which would mean that my main current would be bypassing the first of the resistors and going through, so we've got half as much resistance. And then in my step 3, we would go and have this, this, and this, which would all be closed, and all of my current would be bypassing and heading down to the actual motors itself. We can take what I've drawn inside here. Now, I know that they would all operate at the same time. I'm just using this drawing to go and show the 3 different steps, so please don't think that these are operating at different times. Anytime that we power A1, all the A1s would close. Anytime that we power A2, all the A2s would close. I'm just showing step 1, step 2, step 3 on the power circuit as it corresponds to this control circuit that we are going to go and have over here. And this control circuit is simply the exact same thing as our previous one that we had, other than that we have now added in a second timer. So everything that we did before above that line stays the same. All we've done now is when we've started up our first accelerating coil, we start a second timer, which is then going to go and time out my timer number 2. We'll follow it through. In this one here, once again, we'll just bring power up to where it would normally be stopped inside of my control circuit here. We'll press our start. As soon as we press start, we would then go and apply power through to my starting coil. It goes through my overloads out to the lines over there, and the starting coil is going to go and seal in, as well as it is going to go and apply power to my timing relay number 1. Let's just quickly draw that out here on the side. Start. So I see that my start, we bring in a little blip, and as soon as we bring that blip in, I shall move down further down here. As soon as we press that button, it is going to go and power my S coil, as well as it is going to go and power my TR coil. And the TR coil is then going to go and start its timing. So we've gotten this far here. TR starts its timing. It's got an on-delay set of contacts that's associated with it. And when TR finishes its timing, it is going to go and fire this one over here. And when that one fires, at the end of the time, it is going to go and fire my A1 coil and start up my TR2. So I can go and add those two into this one now. We'll add in our A1 and we will add in TR2 as individual coils down here. A1 fires on when this thing finishes its timing. TR2 fires on at the same time as my A1. And then TR2 is going to go and continue its timing until it finishes its time. And at that point, it's going to go and fire on my last coil, which is going to be my A2. So we'll just draw that one in over here as well. A2, which is, I should maybe draw in this timing here first. Draw the time that's attached to TR2. We'll say that that ends right over there. So this coil over here is going to go and fire on right there. And then they would all continue operating up until the point where we go and take our stop low. So we'll just draw the stop in, last of all here. Stop would normally be closed, so it's normally going to go and be high. And then right over here, when the stop goes low, it would take out my S coil. When my S coil goes out, my TR goes out at the same time. When TR goes out, it would go and open up this one. So the S coil goes out, which would go and open up this TR over here. And in reality, it actually, through this S over here, drops all of these out. But if you want to look at the contact rates, it drops at the TR. The TR would then go and drop out the TR2, etc. So we see all the rest of these dropping out at the exact same time. Once again, just a timing diagram that shows the interaction between when I press my start, how that affects my timers, then how the timer finishing affects my next two coils, and then between how my last timer finishing affects my last coil. This one over here, going back to the previous drawing that we had, we would call this thing we'll start with this one over here. This is going to be startup, which would go and correspond to this over here. So we can just write that in. I'll get a pen. Startup. That's the point of startup. This one over here is going to be step 1. And this point over here would be my step 2 that I would have. Going back to that one there, showing once again at the instant startup, we have not closed those ones, therefore we've got full resistance in there. Step 1, we take out a bit of resistance. Step 2, we take out the last bit of resistance. Okay, we can continue to go and add more and more of these on. You know, if we had to go through 3, 4, 5 different steps, we could go and do so. The only danger is that we lengthen out the amount of acceleration time. We're also going to lengthen out the amount of time that we're going to have current, inrush current running into our motor, and that inrush current can go and affect sometimes other components inside of your circuit. Particularly, what they can go and affect is inrush will affect your overloads. So we do have allowances inside of our Canadian electrical code to go and shunt that stuff out. We also have got a couple of rules that are going to be determined. Let me just zoom out a little bit so we can get the whole rule in there. That are going to go and say that if we have startup positions, we have to go and shut these things down. Starters. This is out of section 28, having different starting and running positions over here. Magnetic motor starters, that's what we're dealing with over here, contactors, having different starting and running positions, that's what we have over here, a start and run, shall be constructed so that they cannot remain in the starting position under normal operating conditions. What we have covered off inside of here definitely does that. You know, when we start up, we go through the startup sequence. However, if I would lose this thing, it could never remain inside there because this timing relay will finish up, which will power through to this one, which will finish up. There's no kind of manual where I have to go and press a button and increment this along and increment this thing along. It's all going to be automatic. And as soon as I would go and lose my circuit over here, hit the stop, I would go and shut them all down simultaneously. The other thing that the code tells us about is going to be in our overloads. Overloads, oh, I just went past it there. 28.310, shunting of overload protection during startup. It says that overload protection, this is where we, protect from having too much inrush into the current, from having too much current that's going through the motor due to load. We are allowed to go and shunt it out or cut it out of the circuit during the starting period, provided that the device by which the protection is shunted out cannot be left in the starting position. So what we just talked about, it cannot stay in the start position, and that the overcurrent device is in the motor circuit during the starting period. So they're talking about the fact that we can go and shunt out the overloads, but we have to go and leave our overcurrent. So our fuses or our breakers do have to stay in there, but if we've got overloads, we're allowed to go and shunt them out, provided that it's automatic that this thing is going to go into a run position, and we would have to put them back in. We'll see that on some of ours later on. We didn't see that inside of any of our drawings that we were dealing with over here. We saw that we always kept all of our overloads themselves in the system, right? I'll just erase this over here so we can see them, but we can see that we have got these ones over here. If I did need to go and shunt these ones out, what I would do is I would go and operate off of my A2 and my A1 that I would go and have, and all I would need to do is I would need to go and bypass these ones with a normally closed set of contacts that is going to be attached to my A2. And what that would allow me to do is that would allow me to divert current around the overloads. The overloads do have a small amount of resistance. That's how they generate heat. So if I would take an A2 normally closed, anytime that A2 has not operated yet, which means that we haven't gotten to our full running stage, I would therefore be able to go and pass current through. So if I'm in startup, I would be able to go and pass like that around there. If I'm in step 1, that would mean I'd have closed this one over here. Then I would have current that would be going through like this. And then if I get all the way over to my step 2 would fire A2, which would close this one and would simultaneously open that one, which would mean that now my current would go and pass through here and down. Note that this would be an interlocked. It would be tied in so that we couldn't, by the time we get to A2, this thing would automatically have to open. Then as soon as we shut this thing down, this would go and reclose once again if it wasn't normally closed. Last thing that we should cover is just going to be primary reactance. Primary reactance is going to be used on high voltages. Primary resistance, where we actually have resistors inside of there that are dissipating heat, we're going to limit those to low voltage motors, underneath that 600 volt range, generally speaking. Once we go up to high voltage motors, and we got loads of motors out there that are operating at 2400, 4160 and stuff like that. Once we get up to those, we are then going to go and use reactors, because reactors are just safer when it comes to high voltage installations. Primary reactors do have 2 issues though. One, they cannot go and drop nearly the same amount of volts off of them. So we're limited drop. We are far easier to go and drop values of volts using our resistors. These are just limited drop. And the other thing is they're going to go and give me a poor power factor. Anytime that I have these things during startup, I'm adding in more XL, which means that I'm going to go and have more VARs L, right? Inductive VARs that I will have. Bars L. And as a result of that, I'm going to have a really crap power factor during startup. Sometimes enough that it's going to go and push the rest of your system into other weird either oscillations that you can have in RC circuits, or it's just going to go and put you into, billing. BC Hydro is monitoring that, and it's all digitally done now through our electronic meters. So it's going to go and apply fines to you as a result of that. Okay, that covers our primary impedance starters. So once again, primary impedance can either be resistance or it can be reactance. And it is going to go and give us closed transitions. What we're always seeing through these, if I go single, if I go through multiple steps at a time, is that there's always a continuous path all the way through. And last of all, if we have got shunting, that's going to go and happen, or if we want, we can go and shunt our overloads during startup, provided it's part of our automatic controls for these. All right, that's this one.